Hello there, thank you very much for joining me today. This is a video about the demonstration of a Marconi microwave radio test set, scalar network analyzer, and today we're going to be doing a full demonstration including measurements and how to use this kind of test instrument as well. There's a whole family of these test sets which is going to be described in the following video. But briefly, we've got the 6200A, which is this radio test set here that you see before you, and then we've also got the 6200B that's got a disk drive in it, and it's got the reflection analyzer at the bottom, a 4-port reflection analyzer, and that allows us to make S parameter measurements on a 4-port system. That is a 6210 that's added at the bottom there, just for reference, in case you're interested later on. And the test sets also have this accessory as well, which comes in handy, which measures things like fault location on waveguides and cables, how far a fault may be from the test port, and also VSWR reflections for antenna systems and things. And then above it we've got another microwave test set which goes up to 46 gigahertz, which is this model, and this is the 6204B radio communications microwave radio test set. So we've got 3 different models here with all different accessories, and that's what we'll go into. But I wanted it to be just a bit more than just a demonstration video to start with, because quite a lot of people sometimes get in touch with me and say, well, why do you want to get into microwave RF? What's the thing about it? You know, it's a difficult hobby to get into, it's quite expensive, you know, and they make quite negative comments sometimes about microwave radio systems and frequency bands, especially when most people are used to working between DC and 1 gigahertz. So I just wanted to talk briefly about that before we get into the full demonstration video. If you're not interested in that talk, then by all means fast forward the video a few minutes and then you'll get to the full demonstration and the measurements that we'll be doing with this test set. But especially for young people and students and university students that are studying microwave RF or electronics engineering, radio frequency engineering, you know, microwaves are very useful. Not only do we cook with them, but let's face it, everything that we use in life deals with microwave radio at some point, whether it's when we're talking on our mobile phones and the backhaul connection between the radio mast and the switching centre that is in the mobile phone network is conveyed via microwave link mostly, because it's very expensive to get fibre to, you know, hilltop radio masts. In addition to that as well, we're all into 5G technology now, or we will be whether we like it or not, and that uses microwave radio frequencies. And again, you know, that's another aspect to it. There's obviously defence arena with radar, and then there's things like weather radar. Offshore oil rigs and things use microwave links to convey all the telephony data and service traffic from shore to offshore. Then we've got satellite communications. I mean, you know, we've got amazing things going on in the world right now, and we've had probes sent into deep space to take pictures of distant galaxies and planets, and they all use microwave radio in order to relay those images back to Earth through the deep space communications network. And indeed we have things like, for example, satellite communications. That's another thing using microwave radio signals, you know, where we can generate a microwave frequency and beam it out through a horn antenna or through another type of parabolic dish antenna to where we need it to go. And of course, in developing countries that don't have fibre across the country like we enjoy in the developed part of the world, that microwave communications spans great distances and is highly reliable, and you can convey thousands of telephone channels down it, video, audio, data, the lot. The bandwidth is quite large. And one of the other things as well I really enjoy about microwave RF and building power amplifiers and making microwave radio transmitters and receivers is the fact that I do moon bounce, where I can send signals to the moon and bounce the signals off the moon, and they will then come down to the other side of the earth and be received. And indeed I have built transmitters which I've used where, you know, you can use a signal source, such as a YIG oscillator, or you know, something like a YIG like this, and then amplify it up and build a transmitter out of something as small as that, and beam the signal to the moon from your garden, an antenna in your garden, and hear yourself come back, you know, a few seconds later with the echo. And you can also bounce signals off the moon and be received. I've been received in Australia at the other side of the world, and I've received other people from all over the world on microwave radio on 10 gigahertz frequency bands. And you know, it's a very nice surprise when you make something that doesn't need a lot of complicated equipment and test gear, and then you can get results like that, you know, bouncing signals off the moon. It's called EME, Earth, Moon, Earth, and I'll put a link in the description as well below this demonstration video, the Marconi microwave test set. But again, you know, there is a lot of areas in microwave radio, in defence, electronic warfare, electronic countermeasures. There are things to do with, for example, wireless networks, backhaul microwave that is used in everything from stock markets through to telephone exchanges, transmitting thousands of telephone conversations down one microwave link from point to point. And again, people don't realise that microwave actually has a lower latency than fibre, and that's primarily one of the reasons why the stock exchanges use microwave, for example, between London and some of the stock exchanges in Europe across the channel. And a lot of these microwave networks are quite secretive, run by organisations which fund these dedicated links so that they can get their sale route to market through the stock exchange quicker than somebody who's traditionally trading on fibre, for example. And there are great advantages to that. And of course, you know, you can have an interesting design, weather radar, defence radar, all kinds of applications, you know, where you can build microwave radio amplifiers. Like this is a microwave power amplifier, 40 watt amplifier. There are lots and lots of avenues you can go into in microwave RF. You can send television pictures, which I often do, on something as simple as a 10 gigahertz gun oscillator, and receive the pictures as well on a modified satellite LNB in a dish. You can build your own oscillators, filters, you know. Again, this is a homemade filter that's made by myself in a little can. You know, you can build microwave filters and such like, and Waveguide components, you know, where we're using those antennas, microwave antennas, all sorts of really, you know, interesting things. And you'd be surprised at what avenues you can go into, from, you know, weird antennas like this, you know, that are used in microwave applications on aircraft, for example, you know, avionics and defence arenas. So you can really get into it as much as you want or as little as you want. And the nice thing about microwaves as well is that there are so many different areas, from medical, defence, telecoms, you know, where we're talking about 5G radio, for example, 5G mobile phone technology. We are, you know, exposed to all areas really. And not only that, you know, things like GPS satellite that uses microwave frequencies, and obviously there are many other things that microwave is used for, not just for cooking, you know. So yes, it's quite an enjoyable hobby if anybody wants to get into it, you know. And I always say to people, especially young people or whatever, that if they want to get into something, then they can start very basic, you know. And you don't need fancy test equipment like this in order to, you know, to enjoy microwave RF measurements. You can use, you know, quite basic equipment that's like that. The wave meters, which I'll do videos on at some point as well, and you can design your own signal amplifiers and such like. So very interesting hobby indeed to get into. And the beauty about microwave as well, design and RF, is that it's actually a PhD subject, which is still taught today. Microwave, for some reason, as just one of the subjects in radio frequency electronics engineering that's still taught in universities around the world, whereas RF engineering for radar, for example, for telecoms networks, for building radio receivers and transmitters, HFV, HFU, HF used to be taught quite widely in colleges and universities, but sadly the decline of it and the throwaway world now needs less maintenance engineers because the products are made cheap and they can be disposed of and replaced. So the great focus now in microwave RF is design, and that's one of the reasons why these test sets were created, which you'll see in the demo video that's coming up, is the fact that, you know, we have microwave designers out there that are given a brief to design a product, and that could be simulated in software such as Microwave Office, AWR, which is another product made by Keysight, which helps designers build circuits such as this and then actually simulate how that circuit will operate before it's actually physically constructed. But nevertheless, even after a product has been made, like an amplifier, a low noise amplifier, power amplifier, an oscillator, filter, whatever, there are instances where an RF engineer has to make adjustments and minor changes because software can't equate for everything. So although there's been a great attempt across the world of RF engineering and microwave radio design to try and de-skill, in my view, the importance of engineers having the knowledge and the experience themselves of doing homebrew, hands-on designs, that I think some of the industry is trying to get everything onto software and simulate it. And it has its advantages and disadvantages. If you're building something like this, it costs a lot to machine a case, you know, it costs a lot for the components, they're very expensive, and to build the board, and when you put it all together, you know, it's fingers crossed, is it going to work, isn't it going to work? Whereas software tends to take about 90% of that uncertainty away. The fact that it can do all the mathematics, the simulations of how the components and the strip lines and the, you know, the tuning circuits will all function, and the elements of that in the design, and then minor changes can be made after the product's been developed, just to tweak it a little bit. So there is an advantage to it, but old cronies like myself do tend to, you know, look back on the good old days when the designer built something from their own intellect and didn't use software, or very, very rarely used any part of the software to simulate it. It was done through experience and knowledge and many years of doing the job. So yeah, that's just a little rundown of it, and there are some publications as well that you can get that are free subscriptions on microwave circuit design, microwave components, some very interesting articles. There's a magazine called Microwave Journal, and it's published once a month, and it's a free subscription for anybody who subscribes. So you can obviously pay for the subscription as well. You can get it free if you're in the industry, and you can register. If you look for Microwave Journal online, they are that's another way of getting into the area and knowing about how components work, and the suppliers and the different types of technologies and designs, etc. So with that, we'll go straight onto the demo video now. The Marconi 6200A microwave radio test set. We'll do some measurements, show the accessories and how things work, and thank you for watching this part of the video, and we'll hand you over to the demo. Hello there, thank you very much for joining me today. On the bench for demonstration today is a Marconi microwave radio test set. These are very unique instruments in comparison to normal radio test sets which many RF engineers come across. This model is a 6200A, and it is widely used in the microwave radio and RF research sector, aerospace, defence, and laboratories all over the world use these scalar network analyzers. And this particular test set was developed by IFR Marconi Aeroflex going back some years. Aeroflex has a current model similar to this which is still available to purchase. Very expensive pieces of equipment. I'm not sure exactly how much they retailed for, but let's put it this way, it was you wouldn't get much change probably out of about £50,000, I don't think, for something like this. Nowadays you can pick these up for littler than £500 second hand and fully working, you know, so a worthy investment if you want to get into the microwave RF. And some people say, well, what do you want to get into microwave RF for, you know, and what's the point in having an instrument that can measure microwaves and what have you? Well, this particular instrument doesn't just measure microwave signals, it also measures signals at HF, VHF, UHF, and obviously right the way up to 20 gigahertz. Its actual frequency range is 10 megahertz to 20 gigahertz, so it's very useful also at other frequencies as well, even if you're not into microwave RF particularly. What's unique about these as well, which is not commonly found on other models of radio test set in the DC to 1 gigahertz range, is that these have YIG oscillators in them, which are very spectrally pure, very high quality signal sources that are used, and that makes them extremely capable when it comes to doing measurements. In addition to that, there's a whole family of these test sets as well that go right up to 46 gigahertz. There's the 6200A, which is this instrument that you see before you, and then there's also a 6200B, which has a disk drive, a floppy disk drive in the side, and then there's also models in between that go up to different frequency ranges, and also a 6204B, which is the highest spec one, which goes up to 46 gigahertz, which has SMA sockets on the front. Now, I've got some blurb here about the instrument, which we're going to have a look at as well as part of the demo, and do some measurements, which I've set up a couple of measurements there. And if I just show you first of all this manual, this gives us a little rundown of what it's about. The Microwave Test Revolution 6200 series, and quite a nice little book which goes into explaining all about, you know, how the test set operates and what it does. There's quite a bit to it. Very comprehensive manual as well that comes with it, which I'll show you in a moment. And you know, nice clear display with all the different measurement options and capability that it does as well. And then we've got all kinds of accessories as well which go onto this instrument, which I'll show you. But there's a specification, and some more specifications for the different models in the range. And then we've got things like accessories that go with it and what they do, and all the different blurb and information on that as well. So, as well as that, we've got a manual here which is the getting started guide for the instrument as well, which gives you a little rundown of how to do certain tests and measurements. Then we've got a manual on scalar detectors, because this instrument takes two different types of detectors. It takes a scalar detector, and then it also takes RF power detectors as well, which we'll look at a bit later in the video of measuring RF power with the inbuilt power meter. But first of all, if we just have a look at this this manual, basically it says here, when I'm not throwing it on the floor, it says that it says the MTS is an economical test solution that is faster and easier to use than a multitude of individual instruments usually associated with microwave measurements. It says its high accuracy ensures that the MTS is equally applicable for design, manufacture and maintenance tasks. Field applications include commissioning and repair of microwave radio links, radar and electronic warfare systems. It says using the programmable voltage stroke current source, swept or static analysis of components and subsystems is available. This opens up a wide variety of new applications. Intelligent markers, automatic pass-fail analysis, a memory card for saving settings and traces, and a macro function to store and replay key pass sequences further extend to the measurement capabilities. It says an intuitive user interface ensures quick learning, fast operation and ease of use. Hard keys access a range of soft key functions. The user is prompted to make the required selections, and help messages are used to guide and assist. It says 4 versions of the microwave tester or MTS are available, all covering a continuous wide frequency range. So they do the 6201, which is 10 MHz to 8 GHz. They do the 6200, which is this model, 10 MHz to 20 GHz. The 6203, 10 MHz to 26.5 GHz. And then the 6204, which goes up to 46 GHz. It says error-corrected reflection coefficient measurements can be made with the addition of a 6210 reflection analyzer. This enables much more accurate measurement of return loss than is possible with a scalar analyzer. The 6210 also includes a time domain software as standard and can display in both, I think it says Cartesian and polar formats. For details, see 6210 datasheet. So it says that it's a fully synthesized sweep generator. Fast synthesized generator combines the speed of analog sweeper with the precision of a synthesizer. Fast sweep times coupled with wide high stability ensures that even narrow filters can be measured with speed, accuracy and confidence. A 400-point sweep can be made in less than 200 milliseconds, allowing interactive tuning without compromising accuracy. It says both start and stop center and span sweep modes may be used, as well as a CW mode for spot frequency measurements. With a step attenuator option, amplitudes can be set from plus 20 dBm down to minus 90 dBm. Low-level harmonics and spurious signals are generated. It says a leveled accuracy of typically plus or minus 0.5 dB and a superior source match means that a second detector to give live reference may be omitted to simplify measurements. And it's a versatile scalar analyzer as well, because it says the 4-input scalar analyzer has a 90 dB dynamic range with excellent linearity. Both AC and DC detection are provided. It says that 2 auto scaling display channels, each capable of displaying up to 2 measurements, are available. Up to 4 live or stored traces may be displayed. Simultaneous measurements, pass band and stop band characteristics is available in uncoupled mode, since each display channel can be set to suit different frequency ranges. It's got an integrated voltage current sources. The programmable voltage current source increases the range of applications so that devices such as voltage controlled oscillators, VCOs, pin diode, modulators and amplifiers can be characterized at fixed or swept voltages and currents. So it does quite a bit, this test set. You know, it's not you know, basic instrument by any stretch of the imagination. It says rapid fault location. Fault location displays return loss against distance. It is especially important for field analysis of antenna feeders, since faults and discontinues in coaxial cables and waveguides can be accurately located and diagnosed. Short range discontinues and faults spaced only a few millimetres apart can also be resolved. It's got an accurate power meter, which means that it can do power measurements made using the Marconi instruments range of 9 power sensors. Power can be measured from minus 70 dBm to plus 35 dBm at frequencies up to 40 GHz. It says high accuracy is assured since a calibrator is included and calibration factor and linearity factor are corrected. An analog meter is also provided to assist when tuning and peaking. Minimum and maximum hold and limit checking provides comprehensive analysis. It says that it's got a multifunction frequency counter. The frequency counter has 2 functions within the MTS. When readout mode is selected, a digital display of frequency is given in 1 Hz resolution. In swept mode, the frequency counter is used to read and then display the frequency graphically. Limit checking is provided for fault monitoring. Maximum and minimum hold display assists frequency drift analysis. When used with a voltage current source, a plot frequency against applied voltage can be obtained. A typical application is automatic oscillator characterization. And again, you know, some of the applications, chap there going to hilltop radio mast in an AT environment, and then obviously in a research field as well, which is often found in microwave designers. Design engineers obviously employ these test instruments to, they get given a brief, you know, to produce a particular product such as a filter, a VCO, an RF amplifier, power amplifier, could be anything really that's RF wise. And as part of that design process and the brief that they're given, they use these instruments then obviously to produce the necessary specification and read that product once it's been developed and made. So quite often an RF design engineer, once they're given a brief to produce a particular type of product, will either use, for example, design software. If you don't design it themselves from their own intellect, they'll use software like Microwave Office via AWR as well. That's another software package which from Keysight, which creates circuits and does all the theory and analysis, and also models it, and not only does that, but it actually emulates what it will do when it's been physically built. But of course, with anything that's physically constructed, such as a filter, even though that might be designed on a piece of software, naturally, once it's been designed and built, it may not operate as it's been characterized or emulated to operate in the software. So, you know, the frequency response might be totally, you know, totally different to what the software says it will be. And so quite often, the RF designer, the engineer that designed the product, has to then go and make minor changes, add extra components, take components away, change things so that it gets the right performance, because there are variables in all metals and substrates and components and cables and factors which software simply can't take into consideration. So yeah, it's quite a comprehensive instrument. I mean, it does quite a bit, you know, make no mistake about it. So it's got a wide range of applications. But again, it's fully it's a very very good instrument. I mean, you can even characterize a VCO, so there's an output on the back. It'll sweep the VCO with voltage, and then obviously you can read that frequency and its linearity and all the data and details about the particular component that you're testing. Same with RF amplifiers, gain, bandwidth, all that kind of thing. So there's a hell of a lot that you can do with it. So that's a brief introduction to microwave radio test sets from the standpoint of Marconi. I've shown you those already. This is the manual for the test set, and as you can see, it's rather a thick, large manual, so lots of bedtime reading, and obviously it'll drive you up the wall reading that. I would have thought after a few hours you probably just think, well, I'll just play around with it anyway, but if you get stuck on making measurements and things, you can always refer to the manual if you can understand it. I've found that it's quite difficult to follow the manual. It's one of these manuals that's written by somebody who's been well versed in doing design work and microwave radio circuit design, and naturally there are quite a bit of basic knowledge that you need prior in order to really use a test set to its full extent. You've got to be really careful with these test sets, because these power sensors that plug into these ports that have scalar sensor and the RF power sensor, they're not like what's on a traditional radio test set where you can transmit lots of RF power into the test set, and you can burn them out very easily as well, so you've got to be so careful when you're making measurements. So that's what we've got. We've got the inputs here for the sensors to connect in, accessories port. That's the calibrator output where we calibrate sensors. We connect them onto there and run calibrate mode. This is a frequency counter input, which I'll demonstrate shortly. And that's the RF gen output, whether it's a single frequency or a swept frequency. So just to show you basically, what I've done is I've set up a bit of a basic measurement here just to give you a general idea, as to what it can do. So I've got a filter here which I've connected up. We're sweeping a frequency here. We're starting at 800 megahertz, and then we're going from 800 megahertz up to 950 megahertz, thereabouts. And then what we're doing then is we're measuring what the filter characteristics are. Now at the top here I've got the frequency counter there if we were to use that, but this is obviously the main measurement. Now this is another thing as well regards to these test sets. They're so sensitive, and the fact that they're used in laboratory or research applications basically means that as the ambient temperature in the room changes, or indeed handling the sensors with your hands, the heat from your hands and things affects its accuracy. So that's the sort of it gives you an idea of how accurate this instrument really is with regards to its measurement capability, where air temperature can actually affect the measurement. So that's serious stuff, that just shows you what we're dealing with here. So again, we've got the test set up. I'm generating a frequency. We've already got a response there. Now you can change, for example, if we just have a little quick rundown, we've got source, for example. That's for setting up the start and stop frequency. You can also, with the source, enter in quite a lot of modes, so you can set the output power in level, which is currently 0 dBm as indicated there, and you can adjust that with the rotary control as well, or you can input a different level. It's entirely up to you. You can set the number of points that we're going to measure this signal, how accurate this is. So we're setting at 401 at the moment. The higher that figure, the more resolution there will be on that signal than there would have been at 401 points. So we're now measuring 1601 points. We've also got the sweep time. We can adjust that. We can either set it to automatic, or we've got manually set user settables. We've got a source mode, so we can either have it a CW, start and stop frequency, a center, span and frequency sweep, power sweep, voltage sweep and current sweep modes. We've also got source functions as well, so we've got things like leveling and frequency standard, RF blanking. So when I set that on, for example, or off, you can see that the waveform changes on the screen. We've got an internal external source, voltage current output for characterising VCOs, CW filter and loop bandwidth, and a source only mode where if we want to generate a spot frequency as well. Under measure, we can select the different inputs on the front, you know, A, B, C, D, etc., and what those sensors do. We've got input ratio, so we can select different sensors there for the ratios. There's counter grade out at the moment because we're obviously using that. Averaging, so we've got averaging as well, which we can set there if we want to on the measurement. We've got smoothing, so we can put smoothing on, and again it's smoothed out the waveform. Likewise, we've got limit checking as well, so you can, if you want to, you can edit the specification for upper and lower frequencies, and then set up error parameters so that if it falls outside that, then it will obviously warn you that, you know, the spec's not reached. And then we've got general setup, go into all kinds of settings in there. Under cal mode, this is where we can calibrate the sensors, do open short cals, path cals, sensor zeroing and detector zeroing, and calibrate the instrument. We can do that from there. Under format, we can read dB, dBm, watts. We can measure VSWR if we're using the reflection analyzer, and volts. So we can do that. Under scaling, we've got auto scale, set scale, set reference level, set reference position, continuous auto scale as well, so it'll adjust the measurement to the right levels automatically. And then of course we've got markers. Now the nice thing about marker functions as well, which I'll get to, is that you can actually set up bandwidth measurements, and it'll give you the bandwidth of the filter. So we can set up marker functions and then do bandwidth, and then we can do search from maximum to minimum. We can do a bandwidth search, and now it'll give us the details as to the bandwidth of the filter automatically, which is quite nice, you know. So we can see the 3 dB points, what the bandwidth is, and the center frequency, and we can also move a marker as well if we want to with the rotary control. And we've got a search markers tracking as well. There's a tracking function on there, so there's that under markers. So we've got marker functions, dB per octave, for example, or off. Bandwidth again there, all markers off, marker functions again. So you can go into all sorts of things. You can set up your markers as well, and you can put multiple markers on and name them. You can do that, and quite a bit that you can do with the markers. Here we can select the measurement as well, so you can go between the different measurements. We can switch measurement off, go to dB power meter if we want to. Got a channel mode, and then we can go, if we want to, we can go to readout, for example. If we have a fault location adapter on, we'll be able to see what would be the faults distance. We could turn off dual channel, for example, and then we can go back to scalar, so we're just getting the bandwidth there. So there's quite a bit that can be done as well. There's memory functions, recall, and what have you as well. There's lots of things that you can get to your memory settings. You can save traces as well in memories, so that you can print them off later, pass and fail, and what have you markers. So there's a wide variety of things that you can do on this test set. As I say, it's a very comprehensive radio test set, and obviously its capabilities are very wide reaching as to what you can use it for. I mean, this is just one little element of it, but you know, if you're designing, you know, RF amplifiers or attenuators, or, you know, really high frequency microwave circuits, then you know, you can see a lot of detail on this that you simply wouldn't get on other instruments. So yeah, I'll set up another measurement, and then I will be on with the next part. Right, so I've set up a measurement where we're measuring RF power meter on 2 channels. If we have 2 detectors plugged in, we've only got 1 on at the moment, but just to demonstrate multiple channels as well that it can deal with. So I've got the power detector on input D connected to the output of the SIGGEN there. We've got 0 dBm output at 2.510 GHz being measured on that, and then obviously being read on there, so it's giving us the accuracy of the signal generator, which is just 0.2 of a dB higher than it actually says it is on the display there. So again, this type of instrument, being the extremely accurate instrument, would be used to calibrate this, for example. So we could then go into calibration mode on that SIGGEN and set the output levels across its frequency range using this detector, which we've calibrated on the instrument's calibration port. So these are extremely accurate calibration references, really, which we can use the test set for doing that, because it's designed for that purpose as well. We've got a frequency counter here. I'm just going to set up a measurement now where I can demonstrate the frequency counter, which is fed in on this input here. So please bear with me a second. Right, we've set up a frequency measurement for the frequency counter. We're generating a 2.5 GHz signal at 0 dBm into the frequency counter input, and then we've got a frequency reading there. Obviously, if I change that to say, for example, 1 GHz and alter that, and naturally the counter moves with it. Now you can set up different resolutions on this as well. So if we go to I think it's counter resolution, you've obviously got all these, so you can set it up to, you know, obviously 1 kHz, 10 kHz, 100 kHz, 1 MHz, 10 MHz, and then 100 MHz, and I think there's more in 1 Hz as well, down to 1 Hz. So that's how accurate it is, really, very accurate indeed, with a number of decimal places that can read. So that gives you a little rundown of the frequency counter operation, and then I'll just show you the what is the detector head now, which I've got. I'll connect this up, which is for fault location as well. I'll put that on next. But yeah, I mean, you can use, for example, when you're measuring forward and reflected impedances, for example, mismatches in circuits, you can use directional couplers like this, one in the forward path, another one in the reverse path, going in the other way, and then you can basically connect these sniffer outputs then to what are your scalar detectors. So these scalar detector would connect into, obviously that on the ports here, and then you're able to measure reflections and all sorts of things, even in high powered circuits, because of the coupling isolation. And again, we've got things like this where we can transfer coaxial coaxial feeders from the outputs into Waveguide. So if we've got equipment that uses Waveguide feeders, for example, then we can transfer coaxial into Waveguide. That's what this does. So what's called a coaxial to Waveguide transition. And this is what's in these test sets that generates the signals. This is a YIG oscillator. And again, if we were to design a circuit using a YIG, we can actually use the output on the rear of a test set to do voltage sweeps on this, to drive this with a voltage, and then the frequency output coming out the SMA, then we can feed into the test set, and then we can analyse its characteristics, which comes immeasurably useful when we're dealing with design situations. If we're designing a circuit that's going to operate in, and we want it to give, say, a fixed output over a given frequency range, we can test that on there and ensure that component meets that specification and what its parameters are. So that gives you a little idea of what we can do with the test set. So I'll connect up the fault location, and then I shall be back with that. Okay, we've now connected the fault head up, the directional fault location head, which is this 6581, 10 MHz to 20 GHz frequency range on it. This does quite a bit actually, not just fault location, it also does return loss as well. And we have a socket here which connects up to the radio test set's microwave test set output, so that's where it gets its signal feed from. We calibrate this as well with just a load for fault location, where we go through a calibration sequence on the test set under cal for this particular fault location mode. So what we've done for this measurement, after I've calibrated this, is we've attached a cable, which is all this lot here, 7 meters of cable, to this port, which is a fault location port here, and we've connected obviously the head up to the 3 inputs on the test set, A, B and C, and now we're ready to do a measurement where we can look at what we've got. So in the bottom of the screen, if I just zoom out a bit, you'll notice just there it tells you how many meters the marker is at, and I've adjusted the marker to show the peak there. So this is basically, we're making a measurement at about 100 megahertz, sorry, that's up to 100 meters, and I've set up a frequency under my source, my frequency entry, where you can select specific frequencies. So obviously if you're dealing with coaxial cables, for example, you can select low frequencies. If you're dealing with waveguides and using a waveguide system, then naturally you would use a higher frequency, because the low frequencies would not transpose through waveguide in the same fashion that they would with a coaxial cable. So if you're using a waveguide that works between sort of 10 and 12 gigahertz, for example, you would obviously select a frequency in that range for the waveguide. But at the moment we're just using standard coaxial cable, which is this bundle here that I've piled up So we are using a lower frequency of about a gigahertz, I think, roughly around about there. So we've got, we can display in meters, or we can display in feet, for example, and it will tell us now where the fault lay, because obviously we've got a 7 meters of cable all in all, with this meter added to it as well, making it 7. That's 6 meters, plus that makes it 7, and we've got an open end. So this will be simulating like a fault condition that would be going up the radio tower. You know, for example, if I show you in the manual here, I can get hold of it as a typical picture, for example. So let's have a look. So for example, if we've got a radio site that's obviously got a microwave dish on it, and we're going up the radio tower, it's great to know roughly whereabouts the fault is on the radio mast. You know, because obviously you can't be scouring up and down the tower, you know, crossing all the different braces on the tower in order to find. So for example, like this, some of the smaller dishes these days have these are called outdoor units, or ODUs. They have a transceiver on the back of the dish, so therefore there's just an IF coaxial cable coming down the tower, but obviously, even though that's not carrying microwave frequencies, it's carrying UHF frequencies as an IF, an intermediate frequency, to the equipment cabin at the bottom of the tower. You tend to find that, yeah, the coaxial cables there can still break, and that's where this still can come in very useful. But likewise, some of the larger dishes, for example, and particularly not just in microwave links but in radar applications, we don't have a transceiver on the back of the dish. We actually have a waveguide coming out the back of the dish, a flexible corrugated waveguide that then goes down the radio tower as a solid waveguide through different flanges, where it connects and bends in different ways, and then into the equipment cabin. So these type of dishes tend to have the transceivers on the back, because these are backhaul microwave links, but radar systems tend not to. And like electronic warfare and EW stuff tends not to have the transceivers on the back of the dish. It tends to be waveguide directly. So again, we can then use that test set in that. So it's quite wide reaching really, what we can use it for. But as you can see here, we've created a measurement where we're sending a signal out sweeping, and it's telling us how many feet or meters we are from the we can select different velocity factors as well of cable and waveguide, so if we know what that data is before we start fault finding on a tower, then we can do it. But we're displaying in meters now, so that no matter where it appears, you know, obviously if it's up a radio, it might come up 20 meters from the base of the tower, so that then you can walk the tower and then obviously find the leak. So that's the peak there, and that's at 6.9 meters roughly, 7 meters. 7 meters there, look. So that's where we've got the strongest reflected signal. So that gives you an idea of the versatility of this test set, how we can use it for waveguide transmissions as well. So, you know, if we've got a waveguide like this, for example, going up the radio tower, and that were to pack in a flange like this where it joins to another, that's a great aid for an aerial rigger that's climbing up the tower, who would then naturally, you know, go and find it. I mean, to give you an idea, if we're looking at a tower as big as this, for example, you know, if you've got the test set down here in the equipment cabin, and it says that it's 100 meters, you know, on that waveform there, 100 meters up the mast, that's a great help to you, because the last thing you want to do is climb all this right the way up to the top, And naturally, if we're broadcasting off a tower such as this with TV and FM high power broadcast signals, we have to then, it's service affecting, we have to turn the transmitter power down for health and safety reasons, obviously due to RF radiation, or we have to take the tower out of service, and there are obviously complication costs there as well involved. So microwave links that are positioned on this tower in multiple positions, if we've got a feeder failure, then it's quite easy then, once we know how many meters, because this is highly accurate, down to millimeters, we can then climb the tower to the appropriate position on the tower to get to these links, and then where the feeders are, the break in the feeder, be it coaxial or waveguide, and then obviously deal with that. And that's the beauty of this instrument, really, with regards to field service. It saves such a lot of time and aggravation doing that, that it would help enormously. And again, even a tower like this, for example, although it's only a short tower, still a lot of work trying to find, when you've got clusters of cables connecting to different dishes and waveguides, it's a very difficult job to try and find that on a tower, in all weather conditions, because don't forget, we're not just working on radio towers in good weather conditions, but also winter, where there's ice and there's bitter winds and high winds and horrible weather conditions and rain and snow and things like that. So to be able to fault find it, to a dish level is excellent news, especially for somebody who works on hilltop radio sites and such like. So yeah, quite interesting little instrument. You can do quite a bit with it, and obviously, if you're doing this kind of work where you're you're on that sort of thing, on hilltop rooftop sites doing things like this, but again, if you're on Emily Moore television transmitter, for example, which is a place I used to work at many moons ago, that's quite a distance. So fortunately, the microwave radio equipment is held up here in the top gantry, and then obviously it's easier to maintain the microwave links. But yeah, so there's all sorts of little bits to it, and naturally, working on such microwave circuits is exceptionally difficult at the best of times, even in good weather. But climbing a tower like this to try and find a fault is a hell of a job, and as you can appreciate, it's a godsend having something like that. Okay, so this is the rear of the microwave radio test set. Just to give you a little overview, we've got the GPIB connector there. We've got some BNC connectors, which are the outputs that are used to control things like VCO circuits and oscillators and characterised pin diodes, etc., like it mentions in the manual. So we've obviously got an external level input, a frequency standard input and output, so we can connect things like atomic frequency standards, GPS lock standards in there. This is a voltage current output, so we can use that then for testing, characterising RF circuits, etc., like VCOs and pin diodes and attenuators and all sorts of things. We've got the parallel printer output as well. Here we've got the luxury data, and then we've got the power. Obviously this can work on low DC volts again in field work, so if you're at hilltop radio sites or something like that, you can run it off DC power if there's no mains. External monitor, so that's like a VGA, VGA output then, obviously to deal with that. Nice thing about this, if there's any fault conditions or anything that happen, it'll tell you if there's a power supply status, if there's an error. There's a battery there for the memory, 3-volt battery, and then we've got an option sticker here which tells us that it's got an optional step attenuator fitted on this one, option 1 and 2. We've got the power supply voltage switch there as well, and we've got an IEC with the fuses. So that's really a rundown of what's on the rear. The fan is quite noisy on these. It's a lot more noisier than other test instruments that are in the workshop, and you certainly know about it when it's been on a while. It sort of don't get on your wires, but you certainly notice it. So you know, that's something to bear in mind when you've got these on for a while in the workshop. It does get a bit wears you down a bit listening to that thing whizzing around all day. So that's a review of the back of the instrument. We'll have a look at the signal generator next as well on the spectrum analyzer, and we'll show you that. Okay, so this is just a demonstration of the CW mode. So it's not sweeping or in the scalar function. This is where you can just generate a carrier. You can also pulse modulate it, which is particularly useful for radar. And obviously you can, by the sockets on the back, connect an external input from a data stream to emulate a radar pulse signal for the right order. So you can do that, but I've set up a CW measurement here as source only mode as well, and we've got that enabled so that it's not pulsing the amplitude of the carrier, and it's not sweeping either. And we've set up a 1 GHz at 0 dBm output there on the test set. And if we have a look at that on the spectrum analyzer, again we've got good spectral purity, which you'd expect from something as good as this. And obviously, as you can see there with the mark at the top middle of the screen there, it's 0.77 dBm, which equates to the losses in the coaxial cable that I'm using at that frequency. But again, you know, you can adjust the output level as well on the instrument, so I can set the output power. And because this has got the step attenuator on it as well, is that it can go really low in RF power, and then with, you know, obviously just like a radio test set would have, like a Marconi 2955, you know, you can adjust the RF level as well as pulse it as well. And so again, it's there's quite a bit to it, you know. It's a very nice instrument. You can do a lot with it, very capable, and it's you know, it's one of these things that's nice to have around in the workshop. Now the nice thing about it is a lot of these test sets are available quite cheaply. Now even if you don't get the probes, the sensor probes that go in, the scalar probes and the power sensor probes, they do come up quite often on auction sites. And because of the fact that you've got an RF generator as well, from, you know, 10 megs to 20 gigahertz, and then you've also got the frequency counter 10 megs to 20 gigahertz. These test sets often retail now around about the £500 mark to £1,000, depending on what you get with it. But what I was going to say is, even if you know, even if it didn't come with the scalar sensors and the power sensor, it's still a worthy buy, because just for the fact that you've got a frequency counter and a SIGGEN, you know, and you can obviously introduce your own modulation through the back, and you can do so many measurements with it as well, just as it is. And I mean, to buy a signal generator that goes up to 20 gigahertz at the dynamic range this can do, you know, you wouldn't be able to get that for £500, and you certainly wouldn't be able to get a frequency counter that goes up to 20 gigahertz for that money either. So even without the accessories that connect in here, I think, in my view anyway, my personal opinion, that it's actually a worthy investment to buy one. And then later on you will find you'll get these accessories, they do come up, and then you can purchase them and plug them in as well. and I'll do another video on the scalar detectors themselves and the power sensors separate to this video, but just wanted to give you an overview of the Marconi microwave radio test sets. And again, a very fine instrument, a research grade, highly accurate laboratory instrument that has so many applications, and so useful to have, especially for getting into RF design, and you're wanting to expand your knowledge in microwave frequencies and microwave radio frequency engineering. This is the instrument to get by far. So I hope you've enjoyed the video. If you like it, please hit the like button, and don't forget to subscribe, please. And there'll be more videos coming as well on other test instruments. So with that, thank you for joining me today, and look forward to seeing you in the next video. Bye bye.